Today I will be talking on more specific topic, which is about the mainstream solar cell technology, which is crystalline silicon solar cells. You know, it's almost lunchtime, so I will try to make it as short as possible. And I would first like to start with the acknowledgement, the contribution from the people to this work. And we have a bunch of scientists and engineers and students contributed to this work. And also we have received funding from different resources, from national resources and also European resources. And we are currently collaborating with major institutions like IMEC Belgium, Fraunhofer, ISE on these topics. Well, let me first start with the standard description of standard solar cell crystalline silicon. I am sure many of you know already the details. A standard cell consists of, is based on a P-type silicon wafer, and on the backside we have a full coverage of aluminum. Aluminum also creates P+ layer on the backside to create a field for the minority carriers. And on the front side we have N-type, heavily doped N-type layer, which is created by phosphorus diffusion, by standard diffusion furnaces, as you see here. And we have also a silicon nitride layer on top, which provides passivation as well as anti-reflection action on the front surface. This is the standard solar cell. And well, of course, in addition, we have silver contacts on the front side and aluminum contacts on the back side. Okay, this is about having about 90% market share in the commercial market today. So everybody is using this type of cells in their solar modules. Well, the efficiency of these cells is in the range of 17 to 20%. So it depends on several things, but the maximum efficiency you can reach is about 20%. If you want to increase, if you want to go beyond this 20%, you should apply some new device architecture. So these different varieties of solar cells based on crystalline silicon have been proposed recently. Among them, I can mention PERC cells, PERC type structures, bifacials, back contact cells, TOPCon cells, tandem cells. So these are all being studied extensively. Some of them have already been transferred to the industry. For instance, PERC cells is becoming industry standard in these years. In the coming year, we are expecting a significant share of PERC type cells in the commercial market. Well, we have also some low-cost approaches in which multicrystalline silicon solar cell is being used. UMG type, which is unpurified silicon, can be applied, and also some new growth technique like quasi-mono multicrystalline cells, and also reducing the amount of silicon is another approach, low-cost approach in improving the performance of solar cells, crystalline silicon cells. Well, in the future, of course, these low-cost concepts should be combined with the high efficiency concept in order to reach lower cost of electricity. Well, I will particularly focus on thin silicon in this talk. Before that, if we look at the cost of ownership for crystalline silicon solar cell, we see that the wafer cost is the majority of the total cost of the crystalline silicon solar cell. Almost half of the cost of the cell comes from the wafer cost. So if you, instead of using bulky silicon, high-cost bulky silicon wafers, you can try to make it thinner. You can try to use thin silicon wafers and reduce the cost and material usage. But this approach has advantages and disadvantages. So when you use thin silicon wafer, you improve the open circuit voltage. Okay, so this is good. But you reduce the light absorption because you have thinner wafer. Because silicon is not a good absorber. So if you reduce the thickness, you lose some of the incoming solar radiation. So as a result, in order to use thin silicon wafers, you need to employ some new light trapping strategies, which can be based on nanostructures on the silicon wafer, which can be like nanowires, nanocones, etc. So these structures can be prepared by several ways. A lot of activities are going on this topic. One of the approaches that we have been using is to use a solution-based etching technique to create surface texturing. So I will be talking about this mainly. So the structuring the surface for light trapping is very important. Well, as you might know, silicon is a high refractive index material, so it reflects almost 40% of the incoming light. So one of the most traditional approach is to cover silicon surface by silicon nitride, which provides anti-reflection on the surface, together with texturing the surface, making some pyramid structures on the surface using a specific chemistry and obtaining results something like this one, and combining silicon nitride and the texturing the surface, you can reach quite good anti-reflection on the surface. But there is some problems. There are some problems here. One of the problems is this: the pyramid formation is not possible for multicrystalline silicon wafers due to the non-uniform crystal orientation. And also, when you reduce the thickness of the silicon wafer, the size of the pyramids is too high, so that you cannot apply to thin silicon wafers this approach. Okay, well, you can also try to find some new nanomaterials that you can put on the surface that can provide some graded index on the surface, so that you don't have any interface. So this approach can work on both multicrystalline and monocrystalline wafer, and it can provide a better light trapping on the surface than this combination of these two systems. So this is what we are trying to find out. So one of the way of creating structures, nanostructures on the surface, is to apply so-called metal-assisted etching. It's a very simple technique. You use silver nanoparticles here, and you create them by a specific solution. And then these silver nanoparticles inject holes into the silicon wafer, so that the oxidation here is enhanced. So you create an oxidation. It's like anodic oxidation on the surface. And the oxides that you create can be etched away using HF solution very easily. So using this technique, so these nano particles go down to the wafer, so creating nanowires on the surface. So applying this, you can reach structures like this one. Okay. And the optical properties of the surface becomes very impressive, as you see. I mean, this wafer is the wafer with silicon nanowires. This one is without. So you see the complete black appearance of the wafer, so that you have reached extremely low reflectivity from the surface. Okay, so the size of the nanowires can be controlled. The length can be controlled by, of course, the etching time and by the temperature. And the shape of the nanowires can be controlled to some extent using different chemistry in the same approach. So using these structures, we try to fabricate solar cells. So we try to apply this approach to industrial size, large area solar cells. You see the pictures. These are the standard cells without nanowires. These are the cells with nanowires. So you see the black appearance. So you can understand just by looking them how the absorption is enhanced, or reflection is reduced. Okay. So we have shown that large area standard solar cells, which is applicable to the industry, can be decorated by using silicon nanowires. this is possible. But the question, of course, is the performance of, how the performance of the cells, how they are reacting to this structure on the surface. Here, you see the IV curves and also the performance parameters of the cells. And the IV cells curves are looking good. I mean, you see that these are applicable, so you can generate some properly behaving solar cells. However, the efficiency of the nanowire decorated cells have been always lower than the standard reference sample. So we have not been able to get higher efficiency. Although we have good optical performance, the electrical performance of the cells are not so good. So this is, of course, the recombination due to the large area that you create. So you destroy the surface in terms of the electrical performance. You create a good optical material, but you don't have a good electrical properties. In order to solve this problem, we played with the chemistry and we tried to change the structure on the surface. So when you look at the chemistry here, you see that the HF concentration is very critical here. If you have high HF concentration, the etching takes place just under the metal nanoparticles immediately. Okay, so the whole generation rate is less than the consumption rate in this case, and this leads to formation of nanowires. However, if you reduce the HF concentration to a certain level, the whole concentration is so high here that they spread around the nanoparticles so that you end up with a structures like this one. So you generate a pyramid-like structures on the surface using the same solution with different HF concentration. So we try to calibrate this system. We found out that for high HF concentration, the reflection is very good, very low. However, the surface is not good for the electrical applications. But for very low HF concentration, you don't create any nanostructures on the surface, so the optical properties are bad. So we need to be somewhere here. So in this region, we have some optimum conditions for the surface structure and for the electrical properties. And another point is that we apply the smoothing etching with KOH, because when you have sharp edges on the surface, you enhance the recombination there. So for this reason, we try to reduce the sharpness on the surface by applying a KOH etching with different durations, so we can come to this point where you have quite nice surface structures on silicon. Okay, and then finally, we apply this new approach to our cells. Here you see, with this new chemistry, we fabricated cells on monocrystalline silicon, crystalline silicon wafer. So you see that we have reached almost the same performance as the standard reference sample. Okay, so we have found the right chemistry for this case. And the efficiencies, I mean, the real efficiency is almost the same here. I mean, the same as the reference wafer. Okay, so results show that even for higher reflection, the nanostructures have higher JSC value, which is an indication of good light trapping. So we have reached an optimum chemistry for a good light trapping condition. Well, but more important result we obtained is for multicrystalline solar cell, because in the case of multicrystalline silicon cell, you don't have any chemistry to create pyramids on the surface. You need an alternative. The industry is now suffering from HF-based, acid-based texturing because it doesn't generate the most favorable, most desirable structure on the surface. So we can create an alternative for this. So for the multicrystalline silicon solar cell, we again produce cells with the standard dimensions, And then we have obtained a good results from the nanotextured silicon cells. As you see, the short circuit current for the nanotextured silicon is higher than standard isotextured cell, which is the industrial technique. So the efficiency is improved from let's say this value 13.8 to 14.28, but it's clear that the improvement is due to the short circuit current, which is expected from a good light trapping condition. So this technique, we have shown that this metal assisted etching technique is applicable to industrial solar cells, particularly to multicrystalline solar cells. So industry, I mean, when you have a monocrystalline silicon cell line, production line, you cannot make multicrystalline cells in that line. You need to have some modification in the equipment. But if you apply this technique, you can use the same line to manufacture both cells. Okay. So what about tin silicon? So when we look at the tin silicon wafer with less than 50 micron, the fabrication of tin silicon, of course, this is not the industrial approach, because here we consume a lot of materials, but this is just to show a proof of concept. So we used potassium hydroxide etching by applying a mask using a nitride layer. We obtain very thin silicon membrane. Okay? So it's flexible, you see, quite flexible, and it becomes transparent to the light, as you see. But you can see more here. Here you see the thickness of silicon wafer ranging from 4 micrometer up to 30 micron. And we illuminate these thin layers from the backside. You see the transparency increases with decreasing thickness. Of course, this is something already expected. And you can also see this from the absorption spectra, starting from the near infrared region and the red region of the spectrum. The absorption decreases with the decreasing thickness. This is also something expected. What we did here is we applied nanowires or nanostructures on the surface. Okay, and the average reflection from 20 micron silicon wafer decreases, of course, with the nanowire texturing on the surface. Okay, you see the height of the length of the nanowire is 0.5 here, 1 micron and 1.5 micron, and we reduce the reflection significantly. We can control the reflection with the length of the nanowires, and you can see this from this absorption spectrum. So the maximum absorption is obtained on the sample with the longest nanowires on the surface. Okay, and this was also applied to solar cell. But making a solar cell with 20 micron thickness wafer is not very easy. It's quite brittle, so you can break very easily, although it has certain flexibility, as you see here. But we were able to make solar cells, and we obtained these IV curves from these thin wafers. The black one is showing the flat cell without any wires, and the others are showing the results with nanowire for the samples with nanowires with a length of 0.5 to 1.5. And you see the short circuit current is increasing again, as you might expect from the light trapping action. So we get higher short circuit current. The efficiencies are generally low. I should admit this. However, we see that we can obtain a significant improvement in the efficiency compared to the flat sample, okay, for certain length of nanowire. So this can be optimized. This is still undergoing. I mean, we are still working on this. Some of the results have been submitted for publication, so I hope that will appear soon in the literature. Okay, so I come to the conclusion. Well, the metal assisted etching is an easy, industrially applicable way of structuring the surface, and it can be adapted easily to industrial lines. And different structures can be made on silicon, nanowires, nanostructures, pyramids. So this depends on your optimization of chemistry and other things. And we observed increase in the short circuit current. Okay? And this is because of the light trapping effect of the nanowires. Okay? And we need, of course, good passivation. Passivation is the most important process in silicon solar cells, because passivation, because you have a large area, you need to passivate the surface very nicely in order to reduce the recombination on the surface. If you have large area, so you have more recombination. So you need a better passivation. So the passivation problem still remains, so we need to solve it. And we have shown that this technique is really an alternative to the present industrial techniques for multicrystalline silicon cells. And we have been successfully applied this etching technique to thin silicon with less than 50 micrometers. Okay, thank you for your attention.